we'll get started here, and given the size of the group, I think everyone's familiar. So I'll touch on a couple of things just for context here, and then we'll just jump into the well import. As many of you are familiar, we have launched this industry study for 2021. This continues to gain momentum. I think we're up to 6 companies now, and it continued to gain more interest. So if you're not from one of those companies, contact myself or Mark for more information. The premise is that we're going to get together a group of operators, each submitting a data set on a parent-child interaction. And ResFrac will model each of those data sets. We have added a variety of mechanisms and will continue to add mechanisms to ResFrac in order to capture those observations in the data sets. And then jointly with all the participants, we'll compare each of those history matches and simulations and look at whether or not we can start narrowing in on why are these signatures different in the Bakken versus the Midland Basin versus Marcellus and other locations of the submitted data. So we're very excited about the study. I think it's going to really yield some breakthrough understandings on frac hits. And moreover, each participant is going to come away with a prescriptive mitigation plan. So the first half of the study is really focused on underlying physical mechanisms. And then the latter half, we're going to focus on mitigation strategies. Are there things we can do while completing the child well, or things to prep the parent well that will yield better results? But of course, those strategies are going to be contingent upon the mechanism that we think is causing damage in the first place. So very excited about this. Again, email myself or Mark if you're interested in finding out more. And then, of course, today we're going to be talking about ResFrac, and everyone here on the call is familiar with ResFrac. It's a fully integrated, fully coupled simulator. So that means when you press go on a simulation, it runs all the way through the entire life cycle of the wells included. So that starts with fracturing and then production, and then you can have child wells or refracs or EOR processes in those wells. So here's an example of a parent-child simulation. I have 2 parent wells that I'm going to frac ahead of time, produce those for 5 years. You can see depletion, and then coming through and fracking the children wells in between. And we can see the production rates of those various well groups, as well as changes in stress around the fractures through time, the distribution of proppant, and of course, distribution of pressure. So in order to get to the point where you can start making those images and analyzing the results, we first need to set up a simulation. And perhaps one of the more complicated aspects of setting up a simulation is putting in the wells and setting up the stages. And this is something that we receive questions on, I would say, from time to time. And so wanted to review the various methods in which we have in ResFrac to import wells, and then show a couple of the new features or capacities that we have added to the code in the last month or 2. I'm going to go through a couple examples starting from a very simple case where we just have a straight line representing our well. And this is suitable if you're doing a thought experiment. So the RTA paper that Mark and I wrote last year, we just used a very simplified well geometry of a straight line because what we're interested in are the dynamics between the fracture and various signatures that would manifest in a rate transient plot. However, if you're doing a more advanced simulation, or you just want the picture to look a little bit more complicated, you may want to actually import the well survey. So we'll show how you can do that. And then some of the new options that we've added give you more flexibility in how you set up the stages and the perforations. So we'll go through those options as well. Switching over to the UI, I created this simulation I called well import. And in it, this first table, so in the wells and perforations panel, you'll see I have one well in my model. It's called well demo. If I open up that well, you'll see I have represented the well as just a straight line along the x-axis. So in these three columns, I specify the x, y, and z vertices that define the trajectory of my wellbore. And in this case, I just have a straight line in the x direction. So to visualize that, I can press the cube up top, which will open up a preview panel. And here you can see that my well is just a L with two straight line segments. And if I hide my matrix and show the perforations, you'll see the perforations are spaced out along the lateral. And so those have been specified in this bottom table below. So I have a couple options of modifying this well or making a new well. So one that's kind of hidden that you may not be familiar with is there is a duplicate well function. So if I press duplicate, it actually just creates a copy of this well. And where this might be helpful is it's a very easy way to just add a second well. So what I'll do is I'll just change the Y vertice to 500 on each of these. And you'll notice I'm just typing it in the top cell, and then I select the row and press Control D, which copies the value all the way through the column. And so if I come back to my preview, I can press refresh. And now you see I have two straight lines. If I hide my matrix again and show my perforations, there's my well set up. So that's a very easy way of adding an additional well. To add more complication, you might choose to import a well using a well survey. So the first thing I'm going to do is I'm going to remove the wells that I have in the model and come back to the first wizard, which is the green button that says Well Survey Import Wizard. Here, I start by giving the well a name, and it has to start with well and then underscore, and I'll call it survey. Let's say survey 1. And then I give it the wellhead a position. So we'll just use the 0 origin. Inner diameter of the wellbore, 4.778 is standard for 5.5-inch casing. And then you have an optional recentering MD. So what this is asking for is if you have a well survey, where would you like the model to be centered along the well? And you specify that using measured depth. So I can put something like 9,000 feet. And then if I come over to my Excel sheet, I have two surveys here. We'll use the left-hand one. You'll see that has measured depth, inclination, and azimuth. I will take those three columns and copy them. Come back to the wellbore survey. All I need to do is add one row. And then when I paste, the UI will dynamically expand this table to the entire length of my pasted region. So now you can see it's expanded for all the rows that I had copied from Excel. And if I press apply, I will now have a well in there. And coming back to my preview, if I refresh it, now you'll see that I have my wellbore that's at a particular trajectory. And then you'll notice that my reservoir region looks a bit odd. It's no longer perpendicular to my wellbore, but instead is kind of cattywampus or lopsided along the wellbore. And that is because we are now kind of in compass coordinates rather than just a artificial coordinate system. So if I come back to static model, one of the things that I will need to do is adjust the direction of SH max. So because I put in my well with a azimuth as reported in the field, I need to also know what the azimuth of SH max is in the field. And if it's 75 degrees from north, as in this case, I can put in 75. And if I come back and refresh, I will see that that wellbore region is now set up along SH max, such that my fractures will propagate along the length of the matrix region. Then my next observation would be that if I'm plotting initial permeability, you'll see that the permeability in which my well is intersecting in my model is all constant at 50 microdarcies, which is not what I recall from the static model I had set up, where I have varying permeability, 50 nanodarcies, where my pay was actually 300 nanodarcies. And the reason for this is that the depths between my well survey and my static model are different. So an easy way to adjust this is to come back to your wells and perforations and choose the second wizard, which is adjust well landing depth. So here I can select my well, choose what zone I want it landed in, which is my pay zone. I can choose whether or not to adjust the matrix region depth, and then I specify a relative position within the zone. So if I want my well in the bottom 3/4 of the zone, I can put in 0.75, press apply. And again, if I come back here and press refresh, now you'll see there's my high perm region and my wellbore is landed in the bottom 3/4 portion. If I open up the well, you'll see I have a long list of points that define my well vertices in that trajectory. And so it can be hard to then specify perforation clusters and stages along that well, which is where at the top, you can see there's an option that says specify using inline method. And what that allows me to do is use this well stages setup wizard. So using this third wizard, my first input is the length along the wellbore that I would like to model. So if I have 250-foot stages and I want to model 3 stages, I would put in 750 feet and then make my stage length 250 and press apply. And now when I open up my well again, you'll see that I have a very easy table where I can just specify the number of clusters per stage. So just to kind of demonstrate visually what's happening, let's put 8 in one stage, 2 in the next, and then 15 clusters in the last stage. And here I would assign how many shots per cluster, the perforation diameter, and coefficient of discharge. So if I come back to my preview, again, I'll need to refresh because I've changed my parameters, and I can take a slice here so I can see both the matrix and my well. And if I zoom in to that wellbore section and show perforations, here we can see there's those 8 perforations per stage, 2, and then 15. However, specifying stages that way, you'll note that each perforation or each cluster has the same number of perforations and diameter, whereas sometimes there's different schemes in how people set up an individual stage. So if you want more control, there's now a wizard up at the top that says Convert Perforation Clusters Wizard. If I click this, what this wizard does is it converts that inline or generic table to a table of XYZ vertices for each of the clusters. So now you can see I have each of my clusters that is specified by an XYZ coordinate. And if I scroll right in this table, I can individually control the number of perforations in that cluster, the perforation diameter, coefficient of discharge, and I can even do things like turn on and off clusters at various times. So you see there's an activation time and shut-off time. Why that might be helpful is if you're doing a ResFrac simulation, you could have your original cluster spacing and then deactivate those and have new cluster spacings if you, say, cemented in a new liner. Now, let's say you had uneven spacing between the stages or the clusters within a stage. If your well bore is at an angle, as this one is, it can sometimes be difficult to modify these coordinates. However, what we're used to looking at is distance along the lateral. So up at the top, you'll see there's another Boolean option that says specify cluster locations using MD instead of XYZ. So if I click this option, and again scroll down, now you'll see that my XYZ columns have become read-only, and instead, I can input values for the measured depth of each perforation. So in our example, I think we had 8, 2, and 15 as the cluster locations. But let's say we had some sort of scheme where we had clusters right next to each other. So for the second one, I could specify 13,325, which is about 4 feet away, and 13,321, and then make a gap. And now we're at 13,235, and we could do 13,231, 13,2. Messed up on the 13,227. I need to correct this one, 13,231. So I don't know why you would do that, but you might have some uneven spacing, and you could modify it directly in this table. And then again, if I come back to my preview, I can refresh, take a slice, and then show my perforations. And now you can see where I've set up that scheme. Oh, let's take a lower slice where I have the clusters grouped together and then another group together. And now I'm back to that original spacing I had set up with the inline method. So all of those options give you almost unlimited flexibility in the ways that you set up a simulation. There's often, we've seen things like football schemes, right, where you might have a lower number of perforations toward the beginning of the stage, and then more in the middle, and then less in the heel. Or you could have a toe biased perforation scheme where you're tapering the number of perforations from the toe to the heel, or vice versa from heel to toe. Any of that is possible with the way that well bores are set up within ResFrac. So with that, I'll pause and see if there's questions or if anyone has a challenge for me in terms of setting up a well bore or perforation scheme.
Hey, Garrett, I'll ask a question. It's not a challenge, just more of a comment, or a question. So when you've looked at a number of simulations that are set up where the well bore is not 90 degrees from maximum horizontal stress, what are the largest implications on results? I'm not talking about like a longitudinal frac, but say something 30 degrees off. Like, what do you see in terms of cluster efficiency, just general comments?
Yeah, it's a great question. And actually, I'm going to stop sharing my screen for 1 second. go into my hard drive and pull out a presentation that I gave a couple months ago. So effectively, what you're talking about, right, is that some people have claimed the optimal orientation for a well, right, is in the azimuth of SH min, such that fractures propagate perpendicular to the wellbore. And so when set up like this, what happens is your cluster spacing is equal to your fracture spacing. So what do I mean by fracture spacing? Fracture spacing is the distance between any two fractures emanating from a cluster. Now, if you rotate that well, so here we're rotating by 45 degrees, the cluster spacing along the lateral is still the same, but now the fracture spacing is lower. So in both these images, X, the distance along the wellbore is the same, but when I rotate by 45 degrees, my fractures are now closer together. And so the impact that has on results then is determined by your reservoir properties. So there are two impacts that I would see there, or have seen commonly. So one is a stress shadowing impact, right? So if indeed fractures are closer together, then it is conceivable that the stress between the fractures is also greater. And so that might impact things like perforation efficiency. If you think about it in the maximum case where well orientation would be 90 degrees, then your fractures are just propagating transversely along the wellbore. And if you try to initiate a new cluster, you're either initiating into a fracture or into maximum stress. So that would be very unfavorable and not very likely. But in that range in between, you may see a higher stress condition in between your clusters, and therefore lower perforation efficiency. Which this image would apply to, right? If we just consider this blue halo a stress shadow, you can see how those stress shadows are closer together when we then tilt the wellbore. The same applies to radius of investigation, right? So your region of pressure depletion is a function of your fluid properties, so the compressibility of the system, as well as the permeability. And so you can be in this case where, from a depletion perspective, these fractures don't talk to each other at 90 degrees, and they don't talk to each other at 45 degrees. However, both with stress or depletion, you could be, say, and this is a case where at higher perm, which would correspond to a higher or larger region of depletion. If that region of depletion is higher, or that stress shadow is larger, then you could be in a case where you start to interfere when that fracture spacing is less than the cluster spacing. And so again, this is a demonstration with simulations where the lateral spacing between the two wells is the same, and the length and the stage length and cluster spacing along the lateral is the same between the two simulations. But what I did is I just rotated the wells by 45 degrees. And in early time, there's not very much difference. So these two, if you plotted the cumulative production versus time, would look the same. However, when you go into late time, what you'll see, and I think this was like 5 years, but again, it's going to be dependent on your reservoir properties. You can see in the case where the fractures are optimally oriented, there is some cluster to cluster interference happening, as indicated by the low pressure. This is in megapascals, so 1 megapascal in between fractures. That's kind of artificially low, but demonstration simulation. It's just getting to that kind of bluish color. Whereas when the fracture spacing is less, you can see that these wells are now interfering much more drastically. And if you were to look at a RTA plot, you would see that these two trends would overlap for early time. And then when these clusters started interfering, you would see a deviation from linear flow and an upward bend in the RTA plot for the right-hand simulation. That's something we look at in field data when we're looking at data sets, and something that we've seen is certainly when you start drilling off azimuth, time to interference at an equivalent cluster spacing can be quicker. And equivalently, in some situations, then cluster efficiency could be lower as well because of stress shadowing. Long-winded answer. Was that the flavor you were looking for?
Yes, exactly. Thank you.
There's a quick question. For if you're going to place a second well, are you going to use just a distance between two wells to place a second well, or are you going to use a coordinate from each well?
So if it's something like well spacing, like if you're doing a sensitivity, one thing that I have done, let's see, played these games before. So if I duplicate my well survey, call that well survey 2. What I can do is you have to do a little bit of geometry in Excel, but you can copy these coordinates into Excel. And then just shift them by a factor, right? So if I do this, well, there's two ways. One, you could actually just shift in the orientation of SH max, right? So you'd do like a cosine of the angle and add that to the y coordinate and the sine and add it to x coordinate. One way of doing it and the most accurate. A cheap method is I could just add the equivalent distance, and again, this would have to be, that 500 would have to be the cosine of the angle that you're trying to add to, or cosine of the angle times the distance that you're trying to have between wells. Paste it in. And we're actually going to switch back to inline. And then I'm also going to do my well stages setup wizard once again. And the reason I'm doing this once again is what I have effectively done is here's my original well, and by adding just a scalar to it, I added a second well, but it's now offset, right? And let's say SH max is something like this. And so if previously my perforations were right here, now when I've shifted the well, they're up here. And so they're no longer within my model. However, if I run the well stages setup wizard again, what it's going to do is it'll center the stages that I'm modeling with respect to SH max. And so like I said, this is kind of a cheater method because the heels of my wells no longer line up as they should. But from the domain of the model, there's going to be a little bit of difference in frictional pressure drop because this is now farther along the well than this stage was. Probably not a huge impact, but and so if I'm just doing something quick, this is the way I do it, is I just add that cosine distance, press apply. And now if I come back to my preview and refresh, you'll see there's my two wells next to each other. And those perforations are lined up. But as you can see, the heels of my wells no longer line up. So it's kind of a quick and dirty way if you're just wanting wells to line up, but truly what I should have done is added a factor to the X and the Y coordinate to make the heels line up nicely. Did that answer it right?
Yeah, thank you.
Cool. Okay. Well, not a giant group today. Well, as always, we'll post the video back online if you want to review. And we'll look forward to 2 weeks from now.